We'll start with a simple line integral example, integrating over a line segment. I'm going to rewrite the curve parametric form, compute the differentials, and plug it all in. So our curve, I got a plane, and another plane. Intersect two planes, you get a line. Make it a line segment, got to restrict its size. So something like this. The fact that I've restricted the x, that suggests that x would be a good parameter choice, because I've already got its domain. So in my two equations, I'm going to solve for the things that aren't x. I'm going to solve for y, I'm going to solve for z. Every equation solves for a variable, and so I start solving. I'll solve the first equation for z, and plug it in the second. Keep my labeling going so I don't get confused about what equation's what. Replace z, collect terms, and solve for y. So there's my second equation. Everywhere y appears, it's now getting replaced. So back in the first equation, collect my algebra, and I've got z in terms of x. There's my two equations rewritten. So now I'm going to write it in parametric form. So I just substitute the equations into the standard parameterization. X equals x, y equals y, z equals z. X is x, y gets replaced, z gets replaced. And there I'm in parametric form. Wrap it in angle brackets, and I get my vector form. Just got to plug it into the integral. C in parametric form. Got to compute my differential. So instead of summing over the points on the curve, I'm going to sum over the parameter values on the curve. Take my derivative. Negative 1/2 squared, 1/2 squared. And now I sum over the parameter values. And there we go. That was my y term that I substituted. There's my z term I substituted. There's my differential I substituted. All of them work like this. The whole key is the parameterization. Once you get your parameterization, it's easy.